and welcome back to my videos for General Chemistry 1. In the last chapter, we talked about how to write the formulas and names of chemical compounds, and in this chapter, we'll start putting that information to good use. Today, we'll be dealing with some of the smallest numbers you'll ever see, and also some of the largest. At the end of the video, we'll end up waist deep in sugar, and on the way, we'll get to see some amazing artwork and find out a bit about the atmosphere of the planet Venus. This chapter is all about finding answers to some of the most common questions chemists want to answer. When we combine chemicals and make them react, how much of each chemical will we need, and how much of the products will we get? This study of the relationship between the amounts of the reactants and products in a chemical reaction is called stoichiometry. Stoichiometry seems like a really odd word, but it just comes from the Greek word stoichion, meaning element. So stoichiometry literally just means measurement of elements. So how do we measure elements? The first big step came in 1763. That was the year that people first realized that the total mass of the reactants must be the same as the mass of the products. In other words, matter can't be created or destroyed. You've probably heard this before. It's called the law of conservation of mass, and it was first proposed by the Russian chemist Mikhail Lomonosov. Lomonosov was a really interesting character. He was interested in just about everything, and he made lots of contributions to both science and art. For example, he was a good astronomer as well as being a chemist, and he was the first person to realize that the planet Venus has an atmosphere. He also came close to coming up with plate tectonics, the idea that the Earth's crust is made of a series of plates that move slowly over time. And he was also a fantastic artist. He made dozens of huge and detailed mosaics, many of which you can still find in museums in Russia. This is his most famous one, called the Battle of Poltava, and it shows the battle that took place between Russia and Sweden in 1709. It's a huge work of art. It's about 15 feet high and 20 feet across, and is entirely composed of tiny pieces of polished colored glass and stone. It must have taken forever to make. The law of conservation of mass that he discovers tells us the number of atoms of each element must be the same before and after a chemical reaction. For example, take this reaction. The balloon contains a mixture of hydrogen gas and oxygen gas. When they're ignited, they combine to form molecules of water. If we write out the chemical reaction, it looks like this. You might remember that way back in the very first video, I told you that some elements pair up so that they exist as diatomic molecules instead of single atoms. If you forgot about that, you might want to go back and re-watch that video. Anyway, hydrogen and oxygen are two of those elements, so their formulas are H2 and O2, and the product is water, H2O. But this reaction breaks the law of conservation of mass the way it's written now. There are two hydrogen atoms on both sides of the arrow, but there are two oxygens on the left side and just one on the right. We know that atoms can't be created or destroyed in a chemical reaction, so this equation must be wrong. In order to fix it, we'll do what's called balancing the reaction. Balancing a reaction just means making changes to it so that the number of atoms for each element is the same on the reactant side as on the product side. How do we do that? Well, what we should not do is add an oxygen to the water molecule. If we do that, it's not a water molecule anymore. When you change or add a subscript to a chemical formula, you're changing what the molecule is, and we must never do that. What we can do is change the number of water molecules. If I add a second water molecule on the right, I'll now have two oxygen atoms on the right side. Unfortunately, by doing that, I messed up our hydrogens. Now there's 2 on the left and 4 on the right. So to fix that, I'll need to add another H2 molecule on the left side. Now there are 4 hydrogens on both sides, and 2 oxygens on both sides, and that means our reaction is balanced. This brings up an important strategy to use when you're balancing a reaction. When you change the number of a molecule in order to balance one of the elements, always go back and recheck the other elements that you had already balanced before, because you may have unbalanced them when you made your last change. Anyway, back to this reaction. It would be strange to write the reaction the way I have it now, with each molecule written out. Instead, we'll combine the two waters and also the two hydrogen molecules. The number we put in front of the molecule is called a coefficient. Let's try another reaction for an example. This time, I'm going to give chemical names instead of the formulas. Based on what we learned in the previous two videos, we should be able to change the words into chemical formulas and use them to write the reaction. Once we do that, we'll balance it. Changing the names of chemicals into their formulas is a skill that you should practice. This is something that you'll be asked to do on tests and quizzes. So, for our reaction, we'll combine hydrochloric acid and magnesium hydroxide. The result will be magnesium chloride and water. So our first job is to figure out the formula for each of these. You might remember that hydrochloric acid is one of the acids I told you about in the last video, which has its own special name. Its formula is HCl. If you haven't learned this list, you should do that soon because we'll use them often from now on. Next is magnesium hydroxide. Since it contains a metal, magnesium, we know it's an ionic compound, and we learned how to write their formulas 2 videos ago. To begin, we have to know what the ions are. Based on where it's located on the periodic table, we can tell that the magnesium has a charge of +2. The hydroxide is one of the polyatomic ions we learned about. Again, if you haven't learned about those yet, you should try to do it soon, because we'll be using these quite a lot. Anyway, the hydroxide has a charge of -1. So, to write the formula of magnesium hydroxide, we'll make sure that the charges cancel out. That means we need 1 magnesium and 2 hydroxides. So, here's our formula. Don't forget to put the hydroxide in parentheses. If you just put the 2 at the end with no parentheses, it looks like you're only doubling the hydrogen, but you want to double the entire hydroxide ion. Okay, next we'll do magnesium chloride. This is another ionic compound with magnesium +2 and also chloride. The periodic table tells us that the chloride has a charge of -1. So, to make the charges cancel out, the formula will have to be MgCl2. And our last molecule is water, which you already know has a formula of H2O. So here's our reaction, and now we just need to balance it. If we count up the number of each of the elements, we find out that there's 1 magnesium atom on each side, but the other 3 elements aren't balanced. It doesn't really matter which element we decide to balance first. I'll balance the chlorine first. There's 1 chlorine on the left and 2 on the right, so we'll need 2 HCl molecules. Next, I'll balance the hydrogen. There's 4 on the left, 2 in the HCl's, and 2 in the magnesium hydroxide. And there's 2 on the right. To balance it, we'll need another water molecule, so we'll change the coefficient on the water to 2. If we add up the number of elements on each side of the reaction now, we find out that there are 4 hydrogens on each side, 2 chlorines on each side, 1 magnesium, and 2 oxygens. So we're done. Every element is balanced, and we deserve a donut. One type of chemical reaction that you'll encounter quite a bit in this course is combustion reactions. You're familiar with combustion. Whenever you burn something, you're seeing a combustion reaction, and all combustion reactions have a few things in common. On the reactant side, you have the fuel, whatever it is that you're burning, plus oxygen. Remember, oxygen is one of the diatomic elements, so it's O2, not just O. On the product side, we'll have carbon dioxide and water vapor. Here's an example. In this reaction, our fuel is CH4. As you can see, this reaction isn't balanced. We have 4 hydrogens and 2 oxygens on the left, but 2 hydrogens and 3 oxygens on the right. For combustion reactions, the easiest order in which to balance the elements is to do the carbon first, then the hydrogen, and the oxygen last. So we'll do it in that order. First, the carbon. There's 1 carbon on each side, so those are already balanced. So we'll move on to the hydrogens next. There are 4 hydrogens on the left and 2 on the right, so we'll need 2 water molecules. Finally, we'll balance the oxygens. There are 2 on the left and 4 on the right, 2 from the CO2 and 2 from the water. So we'll need 2 O2 molecules. Now that we've done that, we have 1 carbon on each side of the reaction, 4 hydrogens, and 4 oxygens. Now let's try a harder one. We'll try a combustion reaction of C6H14. This is a compound called hexane, and it's a major ingredient of gasoline. Since this is a combustion reaction, the second reactant will be oxygen, and the products will be CO2 and water vapor. We'll try to balance this the same way we did the last reaction. So we start by balancing the carbon. There's 6 on the left and 1 on the right, so we need 6 of the CO2 molecules. Next, we'll balance the hydrogen. There are 14 on the left and 2 on the right, so we need 7 water molecules. And last, we'll balance the oxygen. There are 2 on the left and 19 on the right, 12 in the CO2s and 7 in the waters. This time we need to be a little careful. We can't multiply the number of O2 molecules by a whole number and get 19 oxygens. So instead, we'll have to multiply it by a fraction, in this case, 19 over 2. Now our reaction is balanced. We have 6 carbons, 14 hydrogens, and 19 oxygens on each side of the reaction. But unlike our previous examples, one of our coefficients is a fraction. We really shouldn't leave it that way. Remember, the coefficient tells you how many molecules take part in the reaction, and molecules always come in whole numbers. You can't have half of a molecule. So we need to get rid of the fraction. We do that by multiplying all the coefficients by the denominator of the fraction. In this case, that means we'll multiply all the coefficients by 2. If we do that, we get 2 C6H14 molecules, 19 O2 molecules, 12 CO2s, and 14 waters. Here's another chemical reaction. This one's already balanced. In this example, one of the molecules is ozone, O3, and the coefficient on it is 2/3. We need to get rid of the fraction, so we'll multiply all the coefficients by 3. That gives us 3 carbon tetrachloride molecules, 2 ozone molecules, 3 carbon dioxides, and 6 chlorine molecules. This method of balancing chemical reactions is another contribution made by Antoine Lavoisier, who we talked about in a previous video. He also came up with the law of conservation of mass, not long after Mikhail Lomonosov. Lavoisier probably didn't get the idea from Lomonosov, since Russia was a fairly closed society at the time, and scientific news from Russia usually didn't make it to the outside world. We'll use even more of Lavoisier's work in future videos. Now, the law of conservation of mass tells us that the weights of the molecules in a chemical reaction must be the same for the reactants and for the products. So let's talk a little bit more about the masses of molecules. To get the mass of a molecule, we just add together the mass of each atom, which we get from the periodic table. For example, we get the mass of lithium bromide by adding together the mass of lithium, which is 6.941 atomic mass units, or AMU, and bromine, which is 79.904 AMU. When we add these together, we get 86.845 AMU. Now let's do it for calcium oxide. We look up the mass of calcium, which is 40.078 AMU, and oxygen, which is 15.9994 AMU. Notice that these two masses have two different numbers of decimal places. If we add them, we shouldn't just say that the result is 56.0774 AMU, because we have no idea what the fourth decimal place is for the calcium. So we can't say what the fourth decimal in the result would be either. Instead, we have to round it, which gives us just 56.077. That's an important rule of thumb. Whenever you add or subtract numbers, the answer can only go out as many decimal places as the least precise number that you started with. You should always round your answer to make that happen. This is what's known as rounding to the correct number of significant figures. Having the correct number of significant figures is always worth points in my class, so be careful about getting them right. There's one more example of a molecular weight that I want to look at. Here's the compound sulfuric acid. It's another acid whose name and formula I asked you to learn at the end of the last chapter. To get its weight, we look at the masses of hydrogen, sulfur, and oxygen on the periodic table. This time, notice that there are more than one of some of these elements. We have 2 hydrogens and 4 oxygens, so we need to multiply the masses of those 2 elements accordingly. Now, when we add up those masses, we get 98.07928 AMU. But we need to round to the right number of significant figures. Notice that the mass of the hydrogens has 5 decimal places, the sulfur has 3, and the oxygen has 4. Since the least precise mass is the one with 3 decimal places, that's how many our answer should have. So we round it to 98.079 AMU. For now, I have one last comment about significant figures. Suppose that when we calculated the mass of sulfuric acid, it had come to 98.0958 AMU. In that case, to get 3 decimal places, we would have rounded up instead of down. That would have given us a result of 98.080 AMU. Notice that when we give our answer, it needs to have the correct number of significant figures, even if the last digit is a 0. In this case, it would have been wrong to give the answer as just 98.08. This has too few significant figures and would have cost me a point on a quiz or a test. So far, we've been talking about the masses of single molecules, and as you know, molecules are extremely small and light. They're way too small for us to weigh, except using very sensitive and expensive instruments. Usually, we weigh larger amounts of chemicals, which weigh a few grams or so, not just AMUs. It turns out that we can convert between AMUs and grams pretty easily, and we'll do that next time. For now, it's enough to know that the conversion between AMUs and grams is an enormous number. In 1 gram, there are 602 sextillion, 214 quintillion, 199 quadrillion AMUs. This is such a huge number that it's a pain to write it out all the time, so we use scientific notation. 6.022 times 10 to the 23rd. This is called Avogadro's number, and it's a very useful number. We'll use it very often all throughout the course, so you should try to remember it soon. Avogadro's number also has units, and we can express the units in a couple of different ways. As I said, it's the conversion factor between AMUs and grams. In other words, there are 6.022 times 10 to the 23rd AMUs in every gram. So Avogadro's number has units of AMU per gram. It turns out that if we have Avogadro's number of something, whether it's atoms or molecules or anything else, we say that we have a mole of those things. In other words, if we have 6.022 times 10 to the 23rd sodium atoms, we have a mole of sodium atoms. If we have 6.022 times 10 to the 23rd M&Ms, we have a mole of M&Ms. For that reason, another unit we can use for Avogadro's number is molecules per mole. It's hard to grasp just how huge this number really is, but here's one way to think of it. Suppose we have sugar crystals. How much sugar would we need to have in order to have Avogadro's number of sugar crystals? Well, suppose each sugar crystal is a cube, about 1/10 of a millimeter on a side. In that case, 1 mole, Avogadro's number, of sugar crystals would be enough sugar to completely cover the nation of Ukraine to a depth of about 3 feet. Everyone there would be chest deep in sugar. That gives you an idea of how huge Avogadro's number is, and also how small molecules are, because a mole of molecules is usually small enough to fit in your hand. Well, we've talked about a lot of stuff today. We'll get lots of practice on these topics in class, so don't worry if it seems new to you for now. Next time, we'll look more at moles and at Avogadro's number and see what else we can do with them. Until then, have a good week.